In this video lecture, we're going to talk about the speed of sound and the Mach cone. Let's go ahead and take a look at the let's take a look at the picture. The picture I have on the screen here is of a rocket sled, and this rocket sled is traveling at 3,300 miles per hour. It's pretty incredible how fast it is. You can see that there are some bearings on a rail here, and they're just the frictional work being done here makes it such a high temperature. You can see some sparks or fire coming out of it. You see the rocket nozzle at the back end of this that's making the sled go off from right to left here. It's just incredible speeds. They do this kind of rocket testing for a variety of purposes. First of all, just to see how devices, vehicles, things like that will behave at such high speeds, the aerodynamic effects on it. They've done a lot of ejection seat testing from these sorts of things as well, where they'll go up to a certain speed and then eject the seat to see how it performs. They've also done tests to see how just humans respond to such high G-level forces. So they'll put someone on a rocket sled, accelerate them at a very high G level, or then decelerate them at high G levels. So there were some really interesting videos available on the web of that kind of testing. You might want to take a look at it. I'll try to leave some links on the YouTube page where you can take a look at some of those videos. So really neat stuff, dealing with extremely high speeds. So definitely in the compressible flow regime. So let's go ahead and start talking about the speed of sound. This is an important topic when we deal with compressible flows. And the way we'll analyze it is very simple. First of all, the speed of sound is just the speed at which an infinitesimal pressure wave propagates into the surrounding fluid. So when I say an infinitesimal pressure wave, I mean a small pressure disturbance, but one that's extremely small, almost zero. It's very, very small. When we talk about finite pressure waves and how fast they propagate, those are known as shock waves, and they'll actually travel faster than the speed of sound. And the stronger the shock wave, or the larger the pressure difference across the shock, the faster it actually travels. But that's a topic for another lecture. Here we'll just focus on sound waves, or the waves of very small pressure difference across the wave. So the way we'll analyze this is, let's take a look at the left picture here. We have a pressure wave, and I'll draw it as a red line here. It's a very small pressure disturbance, and that pressure change occurs over an infinitesimally small distance. So here we have a sound wave that's propagating off into some stagnant gas, and it's traveling at speed c. We're trying to figure out what that speed c is. So we have some pressure out here and some velocity. So the pressure out here is just atmospheric pressure. And then when the wave passes by, the pressure will change a little bit, the density will change, the temperature will change, but they'll all be very, very small amounts. In addition, there's actually a velocity change in the air that occurs as well. So when the wave passes by, there'll be some flow of air that follows, or flow of gas that follows the wave. It's just a very, very small amount. So we'll put that in here as well. So there's a possibility that we have some, in addition to change in pressure and density and temperature, there could be a change in velocity. To make the problem easier to work with, we're going to change our frame of reference so that we're standing on the wave itself. So in order to do that, what we'll do is we'll just add in the speed of the wave everywhere here. So we'll just transform our frame of reference so that we're adding in the speed of the wave toward the right everywhere, so that the wave looks like it's stationary. So now the wave is stationary, and it looks like the incoming flow is coming from left to right into the wave, and then it's going out of the wave in that direction. The speed of it going out will be the c minus delta v, so that's right there. And as I mentioned before, the pressure and temperature and density all change across that wave. So if we say that the pressure, temperature, and density upstream is just p, t, and rho, then downstream it's going to be p plus delta p, t plus delta t, rho plus delta rho. So we're allowing for changes in properties across that wave. It is, after all, a small pressure wave, so we expect the pressure to change. And we know from the ideal gas law, pressure, temperature, density, they're all related to one another through that ideal gas law. So what we'll do is we'll draw a little control volume around a section of the wave. It's a very, very thin control volume. It just basically hugs the wave on either side of it, and we'll apply conservation of mass in the linear momentum equation to that control volume. And if we do that, I'm not going to go through all the steps of it. If you want to take a look at it, it's in my book style notes. But if you go through that analysis, applying conservation of mass and linear momentum, you'll end up with this expression for the speed of the wave. So this is the speed of the wave squared, change in pressure over the change in density across the wave, times 1 plus the change in density over the upstream density. So those tools that we developed early in the course, conservation of mass, linear momentum, we're using those tools here to analyze more complex relations, right? Like in this case, looking at conditions across the sound wave. Now, you'll see that we have the change in pressure over the change in density here. We know from our thermodynamics that pressure and density and temperature are all related to one another through the ideal gas law. So when we say that we have a change in pressure to the change in density, we need to express how those changes are occurring. Do they occur isothermally, where we're holding the temperature constant? Do they occur isentropically, where the entropy remains constant? Is it something else? So how does that change occur? We need to know something about it. Well, it turns out when you deal with flow across this sound wave, this infinitesimally weak sound pressure wave, that process occurs isentropically. So that's actually turns out to be very important. So that we have this isentropic process. So the change in pressure over the change in density we'll write as a dP over d rho. We'll put that vertical bar with an S here just to indicate that it's an isentropic process. And by the way, when I've gone from the delta to the d, I'm assuming that we're dealing with an infinitesimally weak process. Actually, when I wrote down this equation, and even when I drew these pictures, I didn't assume that the wave was infinitesimally weak yet. I just said that there was a change in velocity and a change in pressure and so on. I didn't say that was very small yet. Where it becomes very small is when I go from this expression down to this one. The deltas become d quantities. And see here you have, this would be like a d rho over rho, but that would be an extremely small quantity over a finite quantity. So it just basically becomes 0. So that's why the delta rho over rho doesn't show up down here, is because the delta rho over rho just becomes d rho over rho, which is infinitesimally small. Now, why is this process isentropic for flow across the sound wave? Well, we're dealing with very small changes here, right? It's a very small pressure change, very small temperature change, very small velocity change. Let me first address temperature changes. So if the change in temperature is very small across the wave, that means any heat transfer effects that occur across through the wave itself are very small, right? Because the temperature gradients are basically 0. It's an infinitesimally small temperature change, so there's really no temperature gradient to drive heat transfer. So that process becomes adiabatic. There's no heat transfer occurring. And in particular, actually, the heat transfer from the surroundings into the control volume would actually occur over these boundaries. I'll just kind of try to sketch them in here. And up here, there is no, the temperature is uniform T up here. So just across that boundary, there is really no temperature gradient. So there's nothing to cause any heat transfer coming across that boundary, right? So we don't have to worry about that. Similarly, downstream here, as we zoom in on this boundary here, there's no heat transfer across that part of the boundary either, because it's all T plus delta T on this side. So there's no heat transfer in or out of that control volume. It's adiabatic. Now let me address the reversibility of the process. So again, the sound wave is infinitesimally weak. So as I already mentioned, there's no real heat transfer through the sound wave itself. So there's no irreversibility due to a finite temperature gradient. You remember back from your thermal course that if you have a finite temperature gradient and heat transfer through that finite temperature gradient, that produces irreversibility. But we wouldn't have that here because the temperature gradient is infinitesimal, so there's really no temperature change. There's no heat transfer occurring through the wave itself. So that won't drive any irreversibility. Similarly, the velocity change through the wave is extremely small, infinitesimally small. And if you remember when we talked about viscous stresses, the viscous stresses are driven by velocity gradients. So if the velocity doesn't change a whole lot through that wave, there is almost a negligible velocity gradient. So the viscous effects are negligible. So we really don't have any viscous effects or any temperature gradient effects in the wave itself, so it's a reversible process. So we have no heat transfer across the control surface, and there's no irreversibility occurring in the wave, so it's reversible. So it's an adiabatic and reversible process, which gives us an isentropic process. So that's where that comes from. So the speed of our wave squared is just how the pressure changes over the change in density, and assuming it's an isentropic process. So we know how the how the pressure and density are related for an ideal gas, and we know specifically how they're related for an isentropic process. So if you remember from the introductory compressible flow lecture, we had an expression that looks something like this. ds is equal to, let me see if I have it written down here, yeah. Cp times dt over t minus r dp over p. We had an expression that looked like that, and then there was another one that involved density, and that one, unfortunately, I don't have written down here. But there was another expression that looks similar to this, right? So we had these expressions for a change in specific entropy in terms of changes in temperature and pressure, and then there's actually one involving density for ideal gases. And if we assume that we're dealing with an isentropic process, then that term is zero, and you'll get a relationship between temperature and pressure. And you can do the same thing between pressure and density. Okay? So we can make use of this expression, and specifically the one for pressure and density, to then find this derivative. And when you go through that process, you'll end up with this expression in the end. So for an ideal gas, the speed of sound in an ideal gas, this is the speed of an infinitesimally weak pressure wave, is equal to the square root of the specific heat ratio, K, the gas constant for that gas, R, and the absolute temperature in the gas. Remember, that has to be an absolute temperature because during the analysis we made use of the ideal gas law. This expression involved the ideal gas law. So that's the speed of sound in an ideal gas. Okay, so air is typically treated as an ideal gas, so this is the speed of sound in air. So you can see that the higher the temperature, the faster the speed of sound. Right? So if you have a hot day and you yell something, it'll travel faster than if it's on a cold day and you yell. It's because it's related to the temperature. It's actually not all that surprising that the speed of sound is related to the temperature, because the temperature is really a measure of the microscopic kinetic energy of molecules bouncing around. So you've got all these molecules in your gas moving around, and the speed with which those things move around is related to their temperature. Now you can imagine that if I perturb, if I make a perturbation to the molecules and they kind of bump, I bump into a molecule, it's going to bump into its neighbor and so on and so forth, and that's how the disturbance gets propagated. But if the faster those molecules move around, the faster that disturbance is going to propagate, right? Because they just bump into their neighbors more quickly. So you can imagine then that the speed of sound should be related to the temperature in some way, because temperature is a measure of the random motion of those molecules. And indeed, it's proportional to the square root of the temperature. So this is the speed at which a infinitesimal pressure wave propagates. If you have a shock wave, which is not infinitesimal, it's a finite pressure change, they actually travel faster than the speed of sound. And you can sort of see that up here. This expression did not involve any statement that the pressure wave was weak at this point. So you can see that if you have a finite change and a stronger and stronger finite change, you'll get a larger and larger delta rho, and it'll just make the speed of sound faster and faster. You can see when we made this infinitesimally small, it disappears down in here. But if it's finite, then you actually get this part contributing and the wave will travel faster. So shock waves actually travel faster than very weak sound waves. All right, so that's the speed of sound. By the way, the first person to derive the speed of sound was actually Isaac Newton, long, long ago. And he actually arrived at an expression that looked like this expression right here, except instead of saying that dp d rho occurs isentropically, he had dp d rho occurs, I think it was isothermally. And so you got a different expression for the speed of sound. It was something like 20% off from the actual speed. We'll allow that. Okay, so Isaac Newton got it wrong, but it's okay. Because the concept of isentropic conditions or entropy didn't really occur for another, 200 years later or something like that. So he did pretty well. All right, so let me give you a few additional notes related to the speed of sound. First of all, again, make sure that you use the absolute temperature when you calculate the speed of sound. Just to kind of give you a kind of rule of thumb numbers, the speed of sound for air at standard conditions is on the order of, I think it's about 340 meters per second, which is about 1,115 feet per second, or about a fifth of a mile per second. So just, kind of on a normal day, you go outside, you yell something that your voice is going to carry at about 340 meters per second, or a fifth of a mile per second. I don't know if you've ever heard of this kind of rule of thumb to figure out how far a storm is away from you. If you see a bolt of lightning and then you count the number of seconds until you hear the thunder, if you take those number of seconds and you divide by 5, that tells you how many miles away the storm is. The reason for that is because of this. The speed of sound is about a fifth of a mile per second. So when you see the lightning, that's virtually instantaneous. And then it takes time for that thunder to propagate over to you. And so you count the number of seconds, divide by 5, and that's how many miles away it is. So it comes down to this. The speed of sound in liquids is about 5 times faster. So the speed of sound in liquids is about 1 mile per second. So much, much faster. Okay. Now the speed of sound in a liquid you cannot find using this expression, the C equals square root of kRT. That's only for ideal gases. Speed of sound in a liquid is, you have to find some other way. We won't cover that. But just generally speaking, the speed of sound in liquids is about 1 mile per second. So 5 times faster, much, much faster. And the speed of sound in solids actually gets pretty complicated. As a rule of thumb, let's just call it 5 miles per second. It's actually quite a bit faster than the speed of sound in a liquid even. The reason I say it gets more complicated is because there are actually different wave speeds for solids. There's not just one wave speed, but there are different kinds of wave speeds, but that's outside the scope of this course. So anyway, much faster speeds in solids. So what's the speed of sound in an incompressible substance, a truly incompressible substance? It's infinite. It's infinite because you can imagine, let's say this pen was truly incompressible. If I push on this end and the pen is incompressible, I'll immediately feel it on the other end, right? If I push on one end, it's immediately felt on the other end, because if it's a truly rigid pen, when I push it on one side, it has to move on the other side. There's no compressibility to it. It's not like a spring. So the speed of sound in an incompressible substance is infinite. Make any perturbation somewhere, it's felt immediately everywhere else. But when you're dealing with an ideal gas like air, it takes some time for perturbations to be felt elsewhere. Okay. All right, let's go ahead and continue on. Now that we've introduced the idea of the speed of sound, let me now introduce the concept of a Mach number. You probably already have heard of Mach numbers before, but we're going to review it here nevertheless. So the Mach number, it's named after Ernst Mach, a famous fluid mechanics guy. We'll give it the symbol MA. It's just defined as the velocity in that flow divided by the speed of sound in the flow. So it's just a dimensionless parameter relating the flow velocity V to the speed of sound in that flow, c. Okay, and if we deal with a Mach number less than, so we're going to have names for different ranges of Mach numbers. So if you deal with a Mach number less than 1, let me put it this way. Less than 1, we call that a subsonic flow. C is the speed of sound, or we call that the sonic speed. So subsonic means it's less than the speed of sound. Equal to 1 is, of course, sonic flow. About equal to 1, so, you know, on the order of maybe, it kind of varies, but let's call it 0.7 to maybe, or maybe 0.9 to 1.1. That's called transonic flow. Right in the range of sonic conditions. Actually, a lot of commercial aircraft fly in the transonic region, slightly subsonic, but you know, parts of the wing actually will go to sonic conditions, or maybe a little bit supersonic. So they fly in the transonic regime. Greater than 1 is called supersonic, faster than the speed of sound. And then sometimes there are additional categories people put onto that. So if it's less than 0.3, Mach number less than 0.3, that's often treated as being an incompressible flow. So if we have a Mach number less than 0.3, we just assume it's incompressible. It's not truly incompressible, but as an engineering approximation, we often say, okay, ignore compressibility, just treat it as being incompressible. So you can see that if you're dealing with air, for example, if your flow is less than about 110 meters per second, then you can just treat it as being incompressible. And we've done that throughout the course. So that's no problem. Many flows are less than 110 meters per second, so it's not an unreasonable assumption. But of course, there are many flows that are faster than 110 meters per second. So with gases, you do have to worry about compressibility, especially when the flow speeds are high. Now, liquids, you know, it's tough to get most liquids, you know, it's tough to get above a Mach number of 0.3 in a liquid. It requires a lot of energy. Okay, so in most liquids, the Mach number is going to be much less than 0.3, so we just treat those as almost always being incompressible. So you don't really have to worry about that. And same sort of thing with solids. The speed of sound is so fast that they're often just treated as being incompressible in a lot of calculations. Okay, anyway, we're not worried about liquids and solids here. It's just gases. And there's another regime. When the Mach number is greater than about, let's just call it 5, then you get what are called hypersonic flows. The exact boundary is a little fuzzy, but greater than about 5, those are highly supersonic flows. We call them hypersonic flows. There you can actually start to get chemical reactions occurring. There's so much energy in the flow that you can get chemical reactions to occur. You might even get dissociation of molecules, like oxygen could break up into different oxygen atoms rather than an oxygen molecule. Stuff like that can occur because there's so much energy in the flow. We're only going to be dealing with subsonic, sonic, and supersonic flows. We're not going to worry about hypersonic flows. Of course, incompressible flows, we've been dealing with that all along. So we won't worry about hypersonic flows. Okay, let's go ahead and continue on. Let me just take a look at my notes here. See if I have anything else I want to say about speed of sound. So just a quick review before we move on. For the speed of sound, again, the speed of sound is the speed at which an infinitesimally weak pressure wave propagates. So just where the pressure changes only a small amount across the wave. The way we derived the speed of sound was we used conservation of mass and the linear momentum equation across the sound wave. So we looked at what's coming into it and what's going out of it. And then from conservation of mass and the linear momentum equations, we arrived at this. We said, okay, the process across that really weak pressure wave is isentropic. So that gave us that expression. And from here, if we're dealing with an ideal gas, we could derive that expression. So remember that because we'll end up using it frequently later in the course. Then we introduced the idea of a Mach number, which is just really a dimensionless flow velocity, and we talked about some of the different flow regimes based on the Mach number. Okay, we're going to use the Mach number often in this course as well. Let me move on and talk about another topic related to this, the thing known as a Mach cone. So the idea is this. Let's say we have a plane. It's right here in the middle of this image, and it's just kind of moving ever so slowly, okay, or just maybe vibrating in place or something. It's making some small pressure disturbances. Those pressure disturbances propagate out at the speed of sound, and since this is kind of not really moving, maybe at most it's moving back and forth, its velocity is 0, but the speed of sound is c, and these waves propagate out. So the first wave to propagate out is this kind of brownish wave on the edge. You can see that it's propagated out. I'm saying that the waves are kind of forming from my object at every delta t. So 3 delta t's ago, this wave was first formed, and now here it is 3 delta t's later. It's just the speed of sound times the time. And then here's another wave that propagated out 2 delta t's ago, and then this is a wave that propagated out 1 delta t ago. So they form circles around the object because the object's not really moving. Okay, so I'm just kind of showing how these pressure waves are propagating out from the object. Now let me go ahead and let the object start moving from left to right. Now here it's moving at a subsonic speed. So here the velocity is less than the speed of sound. The Mach number is less than 1. Okay. Now you can see the object was originally here, right? It was originally here, and then at 1 delta t it's moved here. So you can see that right there. It's 1 delta t, 2 delta t it's here, 3 delta t it's there. So you can start to see that it's moving off to the right. When it was here, the first wave that had propagated out is the brown wave, and 3 delta t's later it's now out here. The second wave propagated out from this point. So 2 delta t's later, it's over here because it's centered around where it was where it originally formed from. The yellow wave originated from this point, so it's only gone out 1 delta t. And then here at this instant in time, the wave that's being generated from that point just hasn't really propagated anywhere yet. But one of the things you start to see is that the sound waves are now starting to kind of bunch up on one another on the upstream side, and then they're spreading out on the downstream side. So you're getting kind of this compression of the waves on the upstream side, and then they're kind of spreading out on the downstream side. This gives rise to the Doppler shift that you hear. You know when like a train is, you have a train whistle and the train's approaching you, it sounds like a high pitch, and then when it goes past you, it's a low pitch. It's because of this effect here, that when the train's approaching you, the sound waves are now starting to kind of get closer and closer to one another, so the frequency the wavelength goes down and the frequency goes up. And then once the train passes by you, you're getting this side of the waves, and the wavelength there is larger, and so you get a lower frequency as a result. So that gives you that Doppler shift effect. Now let's say that we're going at the speed of sound. So our little aircraft is going now at the speed of sound, so the Mach number is equal to 1 in this case. Now you'll get this picture over on the right-hand side. So here is our initial point for the aircraft, and the wave that's formed from here 3 time steps later is now this brown wave. Here's the plane after 1 time step here, and then the wave that's formed from that one is this kind of orange wave. And then here's another time step later, here's the yellow wave that's propagated from that one time step later, and then here's our current instant in time. But you'll see all of the sound waves now have kind of bunched up right on the surface of our little aircraft here. They've all those little infinitesimally weak pressure waves have all started to pile one on top of another. And in fact, this dashed line here is the locus of all the wave fronts. If I kept drawing waves after waves, they would all, the leading edges of them would fall along this line. If I just drew a whole bunch of them. And no sound propagates upstream of that. If I was standing here, I wouldn't hear that aircraft coming because none of the waves can propagate in front of that dashed line. Well, the interesting thing that occurs here is when these infinitesimally weak sound waves all start to pile one on top of another, the sum total of the pressure changes now becomes finite. So instead of being an infinitesimally weak pressure wave, it starts to become a finite pressure wave. So we start to transition from a sound wave into a shock wave. Remember, I've said before that a shock wave is when you have a finite change in pressure across the wave. Well, you have an infinite number of infinitesimally weak waves that have all kind of piled one on top of one another, and so they produce a finite strength wave. So because we have this finite speed of sound, we have the possibility of causing all those waves to pile one on top of another, and that produces our shock wave. So you'll actually get a shock wave that will start to form at the very leading edge of that aircraft there. It still won't be terribly strong because we're only going at a Mach number of 1, but it's right on the edge of becoming a shock wave. Now let's go faster than our wave speed. And we'll get this kind of picture down here. So here, the velocity is faster than the speed of sound, so the Mach number is greater than 1. So now, here's our original starting position of our aircraft, and then here's the wave 3 time steps later. Then we move to this one for the next time step for the aircraft, and its corresponding wave that propagated out from there. Same one here. And then here's at our current instant time. So you can see that the wave fronts all are contained within this cone shape. Remember, this is a 3-dimensional, these are spherical waves, so it's actually 3-dimensional shape. So it's a cone that's formed. You're just seeing a two-dimensional slice. Oops. So you actually get this cone that contains all the sound waves. And we call that cone a Mach cone. It's the locus of all wave fronts. So you actually get kind of an angled shape. So now, if we were standing here, we still wouldn't hear the aircraft, even though it's gone past us. We still wouldn't hear it just yet because the sound waves are all contained within this cone. We have to wait for the cone kind of dashed front here to pass by us before we hear it. So we call this region outside the cone the zone of silence because you can't hear anything yet. And then if you're inside the cone, that's called the zone of action because then you can actually hear it because the sound waves are all contained within that. The angle of that cone is actually related to the Mach number. If you take a look at the geometry here, you'll see the distance from this point to this point is v delta t. It's just moved a distance of the velocity of the aircraft times the 1 time step delta t. And then the distance out to the cone here is just the distance that the sound wave travels. That distance is c times delta t. It's just the speed of sound times delta t. So if you look at that angle alpha, you'll get the sine of alpha is equal to c delta t all over v delta t. Of course, the delta t's cancel out. This will be like 1 over v divided by c. So then sine of alpha is 1 over the Mach number. So you can see that that angle of the Mach cone, alpha, is related to the Mach number of the aircraft as it goes along. So we call this angle alpha the Mach angle. So that Mach angle governs how big that, the cone of action or zone of action is, or the Mach cone size. It's just related to the Mach number. Now this is specifically for infinitesimally weak waves. When you start looking at what are known as oblique shock waves, so an oblique shock is a shock wave that's at an angle. Those are finite pressure waves, and their angle is a little different than these kind of weak pressure waves. Remember, each one of these is a sound wave, so it's very weak. So there's an infinitesimal change in pressure across each of these waves. So the Mach angle is a little bit different than the angle of an oblique shock, but that's fine. Once you get far from the aircraft, then the waves get weaker and weaker. In fact, let me go back. Well, I guess I don't have this picture, but in the previous video, the introductory video for compressible flow, I showed a picture of 2 T-38 supersonic training aircraft. If you look at those, there's shock waves close to the surface of the aircraft, but as you get far away, those shock waves get weaker and weaker, and they eventually become sound waves. And so the angle of the waves will eventually approach the Mach angle. And from that, you should be able to back out what the Mach number is actually of the aircraft. As long as the waves are weak and you can see them, you can determine the Mach angle and then get the Mach number as a result of that. So unfortunately, I don't have that picture handy here, but you might want to try it on your own, looking back at the lecture notes from the previous lecture. Okay, anyway, I think I've covered everything I need to for this topic. So we'll go ahead and end it there. Just make sure you're comfortable with what the speed of sound is, what the Mach number is, because we'll use both of those frequently going forward. So we'll go ahead and end there.